Hello everyone. For the post-lab so far this semester, I've asked pretty similar questions, and if you understand acid-base concepts, polarity, solubility, hydrogen bonding, you probably did very well on the first two post-lab assignments. But if not, and you're struggling, I want to make this video to address some of these misconceptions that I'm seeing on the post-lab. And we're going to talk about these misconceptions in the context of the Fischer esterification, the last lab you had, and you made wintergreen oil in that lab. And I want to first show an acid-base reaction. Your acid-base reaction for the Fischer esterification starts out with your starting material, and you have you actually have three sites that could be protonated. This site, this oxygen here, and this oxygen here. And you ran this reaction under sulfuric acid and methanol. The fact of the matter is, sulfuric acid is very strong, and it will protonate methanol immediately. And I've told my students you don't have to show the protonation of water, the protonation of alcohol, if you're under strong acidic conditions like sulfuric acid or hydrochloric acid. Go ahead and just give me the protonated water or protonated alcohol. And so we have to decide in the first step of the mechanism of the Fischer which oxygen is protonated. And there are a couple ways you could do that. You could think about the availability of the lone pairs, or you could think about how acidic the conjugate acid is, because if you form a very stable conjugate acid, that conjugate acid is not very acidic. But I want to use resonance. And the oxygen that is protonated is this one here. So you show protonation like that, and here's an equilibrium arrow. And let me show you why I want to protonate that oxygen. First of all, it activates the acyl group. It makes actually this carbon here, the one with the dot, more partial positive than the original carbonyl carbon, or let's not call it carbonyl, let's call it acyl carbon. And so this carbon is much more electropositive than this carbon. But I don't want to focus on its activity just yet. I want to focus on why it's that oxygen. It's because there's a resonance structure. And you know that resonance is a stabilizing effect. And the resonance structure is this one here. Okay. And so if you have a molecule that has multiple resonance structures, that molecule is very stable. And hence, we're choosing between protonation here, here, or here. Which one is the most stable situation? It's the one that gives you resonance. And so the resonance structure, in this case, looks like this. And thus, protonation at that site is resonance stabilized. If you protonate the other two oxygens, either one of those, you will not be able to draw a resonance structure that's unique to that protonation site. This resonance structure, or this situation, is unique to protonating at this oxygen. And so that is the first step of the Fischer esterification. You're going to protonate this oxygen here. For the mechanism, I normally don't ask for the resonance. You have to have that in the back of your mind that, yes, there's a resonance structure that makes this pretty stable. That's where the protonation is going to occur. And then you continue on your mechanism. And so the second step, I'm not going to draw the full mechanism, but this is the first step. And the second step is attack. Now, I am going to explain later why this attack is more likely when you have protonation. But for now, let me just show you the attack. See, there's an issue here. I already drew arrows on this molecule to show resonance. Let me get rid of these arrows because I want to draw arrows here to show the reaction for the second step. And so the second step is this. Attack. And let me draw the result. And I will leave you to figure out or to practice. I think Fischer is 6 steps. So you have another 4 steps to get the product. But anyway, what do we get here? We get the addition of the methanol. It's still protonated. So you're going to have to take care of that. And we have that. Okay, that's the second step. All right. This is showing again. Why did I show this? I'm showing resonance stabilization. And let me write that down. Protonation at that oxygen gives me a resonance stabilized product or result. Resonance stabilized. You can say product, but I should say resonance stabilized charged molecule. Okay. The next thing I want to talk about is why is this protonation activating the acyl group? So here we'll talk about activating. The acyl group. Activation for what? Activation for the attack. What attack? This attack right here. This attack. It is more likely that methanol will attack this carbon than it is to attack this carbon over here. And that is because when you protonate an acyl group, let me simplify this a little bit. I'm not going to draw the whole molecule, but let's protonate the acyl group like this. You have another resonance structure that I haven't shown yet. That resonance structure is this. Just push those pi electrons up and you have this molecule here. It's not a very major resonance contributor, but it is important because it does put a plus charge on this carbon here. Now, if I don't protonate, okay, if I don't protonate that group, let's draw that here. Would I have that same resonance structure? Yes, sort of. So let's draw that. But the problem with this is that you form 2 charges. And getting the plus charge on this carbon here is less likely. So I'm going to put on a note here. This resonance here is less likely. Normally you don't want, or normally resonance structures that have 2 charges that are opposite each other is not a very likely resonance structure. You're creating charge, right? You know, charge is destabilizing. You want to decrease charge. You want to spread out charge. And so here, in this situation, we're able to spread out charge. So that does happen readily. So here we spread out charge. Okay, so hopefully I convince you that this resonance structure does exist. Now, the thing is, why is it activating? It's activating because when you draw the hybrid, and what's a hybrid? The hybrid is the combination, I'm trying to find a good color. The hybrid is, oh man, it's going to be purple. The hybrid is the combination of your 2 resonance structures. So here we'll call the hybrid resonance. And the hybrid resonance looks like this. You have a partial double bond, and you have pretty big partial positive character on this carbon along with this oxygen, because we're able to spread out the charge between that atom and this atom. The fact of the matter is, when you protonate this oxygen, this carbon right here has a bigger partial positive than this carbon right here. And that's why protonation of the acyl group makes it more reactive. So it's a little bit not circular logic, but you have to follow a pathway to get to that final conclusion. I like to summarize that conclusion by saying this. When you protonate that acyl group, okay, your partial positive, I'm running out of colors. Where did I get more colors? Oh, there it is. Your partial positive is much bigger. Oh, man. Much bigger than if you don't protonate that oxygen. And so one last color change. Tiny, 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 tiny. Okay, it's still there, okay, but it's much tinier. So again, this is more reactive or more attackable. Okay. Let's summarize the first page of these notes. The first one is, why do we protonate this oxygen? Because by protonating this oxygen, we get a resonance-stabilized conjugate acid. The second point here is, why is protonation good for this reaction? Because it makes methanol attack better this carbon. And how does that happen? It's because when you protonate the acyl group, you have a resonance structure that actually puts a positive charge on this carbon. In this case, true, your positive charge is on this carbon, but this is a lot less likely resonance structure because you are creating charge from a neutral, maybe I should say that, from a neutral molecule. So just a little note, or emphasize that this started as a neutral. That's pretty good, okay? You don't want to create charge from a neutral molecule in a resonance situation. And so the bottom line is mainly this part here. Based on the hybrid, that carbon has a bigger partial positive than this one. Okay. So on your own time, try to finish the other 4 steps of the Fischer esterification. Next, I want to talk about purification. And purification mainly via an acid-base extraction, because this is where people are not understanding how are these molecules being separated from their impurities. That's a huge part of lab, is to not only make the molecule, and I feel like in lecture you're getting a lot of mechanisms, so you know how the molecule's made, but in lab is the only opportunity for us to understand how molecules are purified. You want pure stuff, right? You don't want, for instance, in lecture we've been talking a little bit about hydrogenation of oil, partially hydrogenated oils. Well, there's metal in there. That's metal hydrogenation. You got to purify out the metal, or else you're gonna poison your consumers. So here we're going to talk about acid-base extraction to purify compounds. Okay, with an acid-base extraction, you have organic and aqueous. And let me put those 2 situations here. This should look very familiar. This was in your lab 3 post-lab, organic and aqueous. I'm going to talk mainly in generalities, but then I think we'll have time to look at some specific cases, or at least one specific case. Aqueous, okay, agua, water-based, okay? So when you have 2 layers in the extraction, you have the immiscible organic layer and aqueous layer. We have run extractions with KOH. So in your aqueous layer, it's perfectly fine to write KOH, aqueous, like this. okay? Or you could, not preferable, but some people are drawing a bond, okay? I would not prefer that, but I wouldn't take off points for that. In actuality, what you have is, you have an ionic compound. This is called a salt. Ionic compound equals a salt. And that's this dude here. You have to recognize the metals that are used as cations in salts. For instance, Li plus. I think next comes in the periodic table. Oh boy, Na plus, and then K plus. So if that K is positive, you really have in your aqueous solution a K plus and an OH minus. That's what's literally in your aqueous solution. What I don't like, or what I have been taking points off, if you combine both drawings. This drawing doesn't make any sense. Okay? Because you're trying to show a covalent bond and ionic bond at the same time. So this is no good. Okay? Any one of these is fine. Okay? And I kind of like this because it shows you that it's truly ionic. In the extraction for your wintergreen oil, we didn't use KOH as the base, right? This is basic. Or, let me just write here, this is the base, right? Mainly, predominantly that part. We use, I call it nachos. And so let's practice. Nachos is this. NaHCO3. Okay? But technically, what do I like to show? Technically, you have Na plus and HCO3 minus. Now, if you don't remember what HCO3 minus looks like from general chemistry, that's this. So yeah, you can still draw mechanism arrows because you have this negative charge ready to grab a proton, and you have OH. That's the same thing. So there's your base right here. So it's going to strip off an acidic proton. Okay, and so in your Fischer esterification, I saw your TLC plates. There was an impurity. It was the starting material, unreacted starting material. And so in the middle here, I'm not going to choose sides just yet, but we have the starting material a little bit, right? And you have also your product. And all of you had, as far as I can tell from the TLC, a lot of product. OCH3. And give me 1 second. Okay, OH. From now on, before lab, not after lab, you're going to be quizzed. Anytime we do an extraction or a TLC, you're going to be quizzed pre-lab before we start on the solubility of the starting material, the product, what happens when we do an acid-base extraction, and also how these molecules might run on a TLC plate. Let's focus on the extraction part. And so if you have these two molecules and you mix with nachos, okay, and I'll make it easier for us to visualize. I won't draw the sodium. So we have this, and this is the base. We have to figure out who is the most acidic. Is it that dude? Is it that dude? Or is it this dude, right? Because whoever's the most acidic will react with the base. So that's why, hint, hint, on the post-lab for the Fischer esterification, I gave you pKa's. The pKa for carboxylic acid is 5.0. For the phenol, it's 10.0, right? And this is also 10.0. So who is the most acidic? It is this one right here, okay? That is the proton on the unreacted starting material, by the way. Unreacted starting material. So when you mix these together, okay, and you're trying to find what is the most likely reaction, The most likely reaction is you're going to deprotonate this hydrogen right here. Okay, now look what we get. This might be very helpful for your post-lab, and definitely this is explaining a little bit why or why not you got points on the previous post-lab when I asked what is in the organic and what is in the aqueous. I expected certain molecules. And so let's go back to this extraction down here. And the most likely result of this extraction is what? You'll deprotonate the carboxyl. So here's your O minus. What is the conjugate acid? It's this base that got protonated. So the easiest way to draw that is just add a proton, H2CO3, neutral. You know what went unchanged? This guy, unchanged. So when I'm thinking about your extraction and what goes where, this molecule became charged. That's your starting material without the proton. This goes into the aqueous. Okay? Now, yes, many of you had a little bit of impurity, even after the extraction. But I promise you, without this extraction with nachos, you would have a lot more of the unreacted starting material on your TLC plate. We're able to get the majority into the aqueous. Guess where this guy stays? That stays in the organic because it is still neutral, and it will stay in the organic. In this case, our organic layer was dichloromethane. Was it? Yes, you added dichloromethane to your reaction mixture. Okay, and then obviously aqueous is in water. But what kind of water? Basic water with NaHCO3. And so I know it's a little bit scattered, but look where these molecules are going. Okay, once it's charged, put it in the aqueous. Now, is that always going to be 100% true? No. But the thing that is true all the time is that if you make a neutral molecule charged, I'm not going to guarantee that it goes into the aqueous, but I will guarantee that it will be more water soluble. So if you make a neutral molecule charged, let's put the D back. The charged version, like this one right here, is more water soluble. Okay. The last thing I want to say, this is a little bit extra, but I want you to take notes on this as well. Is there a general rule for water solubility? What if it's not charged? Because there are some molecules that are neutral that are still water soluble. Again, the acid-base idea is that we're taking neutral molecules and making one or more charged so they separate. Look over here. They separated. One went into the organic or stayed in the organic. One, this one here, got converted to go into the aqueous because it's charged. What about neutral molecules? Can they be also aqueous soluble? Yes. And so let me give you an example. So let's say here water soluble, and on this side water insoluble. And so the water soluble, I'm going to say for this lab and for this semester, if your molecule is charged, let's call it water soluble. So let's say any charged ion or molecule. That takes care of these guys over here, right? And you could draw it like this if you want, or like this. but never at the same time. Never bond and ions. So that takes care of those charged ions, but it also takes care of molecules that are charged. That we're going to say always is water soluble. But what else is water soluble? Molecules that have a lot of electronegative atoms compared to the number of carbon atoms. So they have lots of O, N halogens like that, relative to the number of carbon atoms. But so this is where it gets a little bit tricky, because a molecule like methanol, that's water soluble. Ethanol, that's water soluble. But if we have too many carbons, 1, 2, 3, that's insoluble, right? So it's kind of a balance. So, when we talk about TLC, we are comparing the number of oxygens, nitrogens, and fluorines with the number of carbons. But mainly I'm asking you to compare two molecules. And so you're going to have to do some mental math, ask yourself which one has more oxygens and nitrogens compared to the number of carbons. There is no steadfast rule in terms of total number of carbons versus oxygens and nitrogens. So I'm going to give you some examples, and maybe we could come up with a rule ourselves. For instance, so those are alcohols. What if we have carbonyl groups? So that is water soluble. That's water soluble. But once we get up to 4 carbons, but if we get up to 4 carbons like this, that's not water soluble. And actually, I fibbed a little bit. 1, 2, 3, 4, 1, 2, 3. We'll put 4 carbons here. Propanol is water soluble, so I'll put 3 carbons there. Okay. I tried to come up with a rule. It's still very, very hard to make this prediction, like whether a molecule is water soluble or not. You could always make the prediction one is more water soluble than another, when you're comparing molecules, but it's hard to tell if a molecule by itself, without comparison, is either water soluble or not. But I think if you take the number of oxygens, nitrogens, and fluorines and multiply it by 2, if did I say multiply by 2? Give me 1 second. Multiply it by 3, actually. Okay, this is a very general rule. And if that number is greater than the number of carbons, you could relatively say that it is water soluble. Now, if carbon is vastly outnumbering your oxygen, nitrogen, fluorine, even if you multiply by 3, carbon is still greater than, then we're going to say that it's probably water insoluble. Okay? Will you ever have to make that decision? Will you ever have to use this rule? Not really, because I'm always asking you a comparison. Who is more water soluble? This molecule or this molecule? Well, this molecule has an extra carbon, and we removed an OH group. So this molecule is less soluble in water than this molecule. I'll always ask you a comparison. I'll never ask you, is this molecule straight up water soluble or not? I will always ask you, which is more water soluble? And it goes to, and it's the same thing as polarity. I don't like asking, is this molecule polar or nonpolar? I mostly ask which molecule is more polar or which molecule is less polar. So I hope you see a difference and you don't, panic about what I might ask. It will always be a comparison. Okay, that's all I want to say here. Hopefully hopefully this answers some of your misconceptions that you've had on the first 2 post labs. This is going to be definitely helpful for your 3rd post lab, the one on the wintergreen oil and Fischer esterification.